In the last video, we took a look at Newton's law of universal gravitation and how we could use it to do things like weigh stars and planets. We're going to be transitioning now to looking more at rotational motion of rigid objects. And to that end, I need to introduce the rigid body model. And I'll start by saying that it is an approximation. And here's where I'm going with that. So I've got drawn here, as I'm imagining a bicycle wheel. And yeah, I only drew in 4 spokes. But what I want you to think about here is, let's say that you have the bike wheel initially at rest. You crank down on the pedals, and now the bike wheel is rotating at some angular velocity omega. So the question is how does this chunk of tire right here know to go around in a circle? And the answer is it doesn't. Let's just start by looking purely at the case where we're rotating at constant speed. So at the top here, this piece of tire would have to be moving forward with some velocity v. And by Newton's first law of motion, it's going to want to keep moving in a straight line at a constant speed. But what's that going to do? So as our chunk of bike tire moves forward in a bit of a straight line, what this means is that the spoke actually had to get a little bit longer. Not showing that as well as I would like. Let's try that again. Yeah, let's just overdraw it like that. So the point I'm trying to get at is that this spoke got a little bit longer. Now, for a typical bike that you or I would be likely to ride, it gets longer, but it's not really a big deal. But for racing bikes, this is actually something they have to take into account to make sure that there's enough clearance. So the spoke got longer, and what does that mean? Well, the spoke wants to return back to its original length. So as a result, that means that the spoke exerts a force due to tension on that chunk of the rim, and so the rim will go around in a circle. Now, let's also think about, I was mentioning, let's think about initially being at a stop and working our way up to omega. So in that case, how'd this chunk of tire know how to go faster? Again, it's the same kind of deal. The only way it could go faster is if it were to have somehow accelerated forward, right? And if it were accelerating forward, it'd have to be that there was something exerting a force going forward. But how could that be? Well, when you mash down on the pedals, you are causing the cog set in the back wheel to move forward. The rest of the spoke didn't get the memo about that. And as a result, because of, by Newton's first law of motion, it's trying to do what it has been doing. So as a result, the bottom bit goes forward, and we end up deflecting. Here, let me draw it in a different color. We end up having the bike spoke being deflected a bit like that. So here, let me just continue it out. So this is compared to if we were just rotating at a constant speed, it would be straight, although lengthened. But here where we're picking up some speed, the spoke actually flexes a bit. And again, it's trying to return to its original shape. And so as a result, it's going to again be applying a component of tension that way. It's actually not tension. We'll just say it's a force. Technically, it's a shear. So we're applying, the spoke is applying a bit of a force to, applying force to make the rim pick up speed. So the end result of this is that definitely if you are increasing or decreasing your rate of angular rotation, parts of the object have to change shape. And even if you're churning at a constant speed, the thing actually got a bit bigger. You can think of the extreme of someone tossing a pizza. You know, the pizza dough stretches out. And so this is true not just for bike wheels, but you can extend this to literally anything. And so the key thought is that there is no rotation without deformation. So for anything to rotate, even if it's just rotating at a constant angular velocity, that object is not the same shape it was if it weren't rotating. So what the rigid body approximation says, though, is that in a lot of cases, for instance, you and me riding a typical consumer bike wheel, while there is deformation, it's not very noticeable. Again, if you're designing a race bike for a professional cyclist, then that would be a different story, and you'd have to use techniques like finite element analysis to handle the deformations that occur. But in a lot of situations, you can just acknowledge in your heart of hearts that the deformation is actually happening, but that it's so small it doesn't particularly matter. So the rigid body approximation is saying that even though we know deformation really happens when something's rotating, we're going to pretend that it doesn't. So if you go ahead and make that, pretend that, you can then think about something like, say, if you were to toss a pencil and give it a bit of a backflip or something while you toss it. There is a spiffy little theorem that's beyond the scope of this course that says if the object is rigid, you can completely treat the motion as a combination of the translation of its center of mass and its rotation about its center of mass. In the next video, we'll rigorously define center of mass. For now, we can just say it's the point where it would balance if you were to try to balance it like a teeter-totter. So there is this result beyond the scope of this treatment that says that if the object is rigid, then you can treat it as just purely the translation of its center of mass, which is what we've been doing so far, combined with rotation about its center of mass. So it greatly reduces the number of variables that you have to keep track of. If you have deformation in your rotation, then it turns out what you have to do is treat this on an atom by atom basis. And that's too hard. So usually what's done is a computational trick called finite element analysis, where you look at groups of a few zillion atoms or so, very small chunks, treat them like little point masses that are interacting with each other. Even so, to properly do this requires substantial computational resources. And so you only really want to do it if you have to do it. So if you've got an object like, say, your pencil, yeah, when you gave the pencil a backflip and let it go flying, the pencil did get the tiniest bit longer, but you're not going to be able to observe that in practice. And so by doing that, you can take it from having to think about potentially millions of variables down to usually 3, although in pathological cases beyond the scope of this treatment, maybe 6 variables. So it's a huge improvement, and that's why we make this approximation. It's valid in many, many situations. Any most solid objects, unless they're jello, will qualify in most situations. And it is a lot easier to do. So with that, we have to now start to think about how the rotation might change. We've already alluded to the fact that the rate of rotation might increase or decrease. So to that end, we're going to have to extend our collection of rotational variables. So far, we've seen angular position. The usual symbol is theta, and the usual unit is radians. And we've seen angular velocity. It would be, the usual symbol there is omega, and that is the time rate of change of the angular position, or the angular displacement over the change in time. Typical units are going to be radians per second. And again, remember, radian is just a placeholder that reminds you that you're dealing with angles, but it actually has no physical dimension. So when you're checking your units, you always replace it with the number 1. So in analogy, we can define angular acceleration. So, whoa, that's terrible. Let's try that again. It's a little better. So the angular acceleration is defined to be the time rate of change of the angular velocity. And the typical units are going to be radians per second squared. This funny little letter here is supposed to be a lowercase Greek alpha. So going back to the paper that we usually used in 2nd and 3rd grade to learn how to write, you would draw an alpha something like that, and then you resist with all your might the urge to turn it into a little fishy. Since I apparently did not succeed in resisting that, I'll make that go away. All right. So let's think about what the signs of angular acceleration would mean. So if the sign is positive, then we're going to be interpreting this as omega becoming more positive. And more positive would mean more counterclockwise. So there are 2 possibilities. Possibility number 1 is that you're already turning counterclockwise and you speed up. Possibility number 2, you're already turning counterclockwise and you speed up. Possibility number 2 would be that you're turning clockwise and you slow down. Turning at a slower rate clockwise is more counterclockwise than what you were doing before. Similarly, if the sign is negative, then we're going to take that, and again, this is assuming that you've made the default choice of counterclockwise being positive. This would mean that omega is becoming more clockwise. So there are two possibilities again here. One possibility is that you're rotating slowly clockwise, and then you speed up. The other possibility is that you're rotating kind of quick counterclockwise, and then you slow down. Because again, turning counterclockwise more slowly than you were before is more clockwise than you had. Okay. So with this, we can go and finally relate to the linear acceleration of an object. So let's think that you've got an object, maybe a rubber ball or something, tied onto the end of a string. If you're whipping it around, making it go faster, follow your hand. If you look at your hand as you whip it around, making it go faster, you'll notice that your hand is not in the center of the circle, but it actually runs a bit in front. So let's say this is the circle that we're following, and we're spinning this around and making it go faster. In that case, the string, if this is the center of curvature here, the string is actually going to be doing something like this. And we can break the acceleration into two pieces. So the force due to tension will be pointed like this. And similarly, the acceleration would be pointed the same kind of way. And we break it into two pieces here. So the one piece that we'll have is the centripetal piece that we saw before. That will be equal to r omega squared. But now there's this new piece here, the tangential acceleration. So this piece here was just responsible for changing the direction of motion. This piece here is responsible for speeding it up. So we can follow that through to get what it is. So the tangential component of the acceleration, a sub t, that would be the change in the tangential speed with respect to time. But the tangential speed is the change in in r omega over time. But under the rigid body approximation, the radius of the circle isn't going to change. So the change in r times omega is the same thing as r times the change in omega. So we write that as r times the change in angular velocity over time to get that the tangential acceleration is equal to r alpha. So then to get the complete acceleration, if you need the magnitude of it, you would use the Pythagorean theorem, square this, add them together, take the square root. Okay. So if you look at the definitions, you'll see that the definitions seem very similar to what we did with translational variables. So position was x, this was v, this was a. Now these are not the same thing, but they're defined the same kind of way, thus the similarity in naming to call that into attention. So since they're defined the same way, this means that there is another gang of four, and this is for situations where the angular acceleration is a constant. We call this rotational kinematics. So again, the key assumption here is that the angular acceleration is a constant. If it's not, you either need to be more clever and or use the methods of calculus. But if the angular acceleration is a constant, in a lot of cases it is, we can go ahead and write another gang of 4. So what we'll have is omega final equals omega initial plus alpha delta t. That would be missing, oops, try that up here, missing theta. Similarly, we have a missing omega final that looks like theta final equals theta initial plus omega initial delta t plus 1/2 alpha delta t squared. We have a missing alpha. And we can do this purely because since it's defined the same, all we have to do is just swap the letters. We got these results before. So theta final equals theta initial plus 1/2 omega initial plus omega final delta t. And finally, if what's missing is the time, we'll have omega final squared equals omega initial squared plus 2 alpha theta final minus theta initial. And so to do rotational kinematic problems, you'll do all the same processes that you would do before when they were translational. But now we're talking about rotations instead of translations. But the process is the same. So let's think about, as an example here, let's say you have merry-go-round. So let's say initially it has a period of rotation of 4 seconds. We'll say it's rotating counterclockwise, and we'll say that it comes to a stop after 20 seconds have elapsed. What I'd like to know is how many revolutions did it make? So we can set the initial angular position to be 0 and say this is tantamount, equals 0, and say this is tantamount to solving for theta final. So at first you might think, well, let's see, we're being asked for the final position, cool, and we're given the time. Oh crap, it looks like we're short 2 variables. We weren't given the angular acceleration, and we don't seem to be given an initial velocity, except we are. This t initial here, this period, we can get omega initial, the angular velocity, by saying, hey, this is saying that in 4 seconds it turned 2 pi radians. So it's 2 pi over radians over 4 seconds is saying it was initially turning at pi over 2 rad per second. So now with that, we're good. We've got omega, we've got t, and we've got theta, or we're asked for theta final. So alpha is neither asked for nor given. So we have theta final equals theta initial plus 1/2 omega initial plus omega final delta t. And we can go and stick in our zeros. Theta initial is 0, theta final is 0. So we get that it's 1/2 omega initial delta t. So it's 1/2 times our pi over 2 rad per second times 20 seconds. So that's all well and good, but Then we can work with that to get, let's see, this is 2 cancels that, that's 10, cancels that, that's 5. We get, and seconds cancel. So we get 5 pi rad, but they asked for revolutions. So we'll have to unit convert. And we remember that there are 2 pi rad in a revolution. So the pi's cancel, we get 5 halves, or 2.5 revolutions. Alrighty. In the next video, we will spend some time defining the center of mass so that we can have a good handle on what it is that we're rotating about. Catch you in the next one.